So we ended last day by saying this. The magnetic force on a charge is QVB, where Q was the magnitude of the charge, V was how fast, the speed of the charge, and B was the magnitude of the magnetic field. We said these two here, which are technically direction vectors, they have to be at 90 degrees to each other. They have to be perpendicular to each other. In fact, Courtney often will just say in the word problem, rather than giving you a diagram, we'll say, hits the magnetic field perpendicularly. Oh, okay, they're at 90 degrees to each other. So consider this electron here. Which way is this electron moving? To the right? Okay, our right-hand rule doesn't work for electrons. Which way is the proton moving? If an electron is moving to the right, it's the same as a proton moving to the... Point your right thumbs to the left, please. Which way is this magnetic field? What do these symbols mean? Into the page, so extend your fingers into your paper or into my board if you're using this as your frame of reference. Right when this electron gets to here, which way will it feel a force, Carson? Down the page, it's going to get deflected, and now it's going to be traveling this way. So now point your thumbs that way. Let me erase that. Magnetic field still into the page. Which way will it feel a force now? And I think now it's going to get deflected this way, this way, this way, this way. In fact, hey, it's going to be forced into a circle. At least a half circle. Maybe more than that if we set up a different kind of an apparatus. Is that okay, Brendan? What's it going to get forced into, Brendan? What path is this electron tracing out? Where is the net force toward the... This is good review of circular motion, by the way. And Brendan, what it means is we can say this. The magnetic force must be equal to the circular force because it's moving in a circle. Magnetic force, Justin, we said was circular force is MAC, and AC, there was two expressions. The one we're going to be using is the V squared over R, not the 4 pi squared R over T squared. The observant ones among you, Ashley, may notice, A, you got one V over here, two V's over here. If you divide both sides by V, Mr. Dueck, one of the V's cancels, and I say, yeah, actually, we end up with this. I don't memorize this. I know this, Carissa, and I always rederive it because it takes all of 1 second, and it's a good review towards the end of the year to remember what the circular motion equation is. Oh, little side nerdy note. What's MV? What is mass times velocity? Ah, Rob. Momentum. I've seen this equation sometimes given as QB equals momentum divided by the radius. Whatever. The point being here, Jessica, if I know any 1, 2, 3, 4 of these, I can find the fifth one. This allows us to start to figure out either masses of really light particles or charges on really light particles, like this. An electron moving at 3.2 times 10 to the 6th meters per second enters a perpendicular 0.545 Tesla magnetic field and traces out a circular path. What's its radius? I would start out, Shannon, by saying I know that the magnetic force is what's pushing it in a circle. The magnetic force on a charge is QVB. And when you're moving in a circle, that's mv squared over r. I would smile, Hisham, and say, yay, one of my v's cancels. And what am I asking you to find here, Hisham? Get the r by itself. Over, careful. I think you said it wrong. You may have thought it right. Over what? QB, yes. This means at the Large Hadron Collider, they can very accurately force whatever charge they want into whatever radius they want by changing how fast it's going. We'll talk about how they control the speed, but certainly by changing the magnetic field. And we have very good control over magnetic field strengths. How? Give me 10 minutes. Anyways, mass. It's an electron. Right at you. Negative 31? Yeah. Speed, they told me. Divided by Q. It's an electron. Ignore the negative. We're going scalar because we want a positive radius. And the magnetic field is in Tesla's 0.545. Now, I made these numbers up. They're not great numbers because you're going to get a really, really small radius. The magnetic field strength that I made up here is way too strong. You recall we watched a video yesterday of a 40 Tesla magnetic field, and that was ripping apart a stapler in a chair. This is only 0.5 Teslas. That's still huge. But what do you get? Now, my morning grade 12s were out to lunch because everyone got the wrong answer. They all forgot to put the bottom in brackets because there's 2 numbers in the denominator. Of course, none of you will forget to do such a trivial grade 8 kind of a mistake. Spence, what'd you get? Oh, still typing? Anyone? Yeah? Which is way too small a radius. I made up bad numbers. Go ahead. I should have had this coming in faster and had the magnetic field smaller, and that would have given me a bigger radius. So then I stole a question that had better data. It's less interesting to find the radius. It's much more interesting if you know the radius, what can you discover or figure out? And they could measure the radius. Now they do it all electronically. Back in the old days, they would use something as simple as they would expose film to the electron. Remember old, like actual pictures back when you took pictures on film? And the electron would carve a phosphorescent circular path on a piece of film. So when you developed it, you would literally physically just measure the radius. It was an arc length question for those of you who have done trig. It was A equals R theta. You knew the arc length. You wanted to find R. As shown in the above diagram, a proton, let's underline the word proton. That's probably fairly important. Entered a magnetic field at location A. The radius was 3.25 meters when the magnetic field strength was that big. What's the proton's speed? What path is this proton tracing out, Carissa? Well, then I would write down the magnetic force is pushing it in a circle. I would say to myself, I know the magnetic force is QVB and circular force is MV squared over R. What are they asking me to find in this question, Alex? Get the V by itself for me, kiddo. Q. It's a proton. 1.6 times 10 to the negative 19. B. They told me 0.02. That's what 2 times 10 to the negative 2 is. That's easier to type. R. 3.25. Mass. It's a proton. 1.67 times 10 to the negative 27. Is that right, Jess? Keeping in mind that if you get anything times 10 to the 8th, 3 times 10 to the 8th is the speed of light. We can't go faster than that. What's V? What do you get? .23. Oh, no, it's not going to be to the negative 14. That means it's hardly moving. No, you're going to get a big velocity, like 10 to the 6th or 10 to the 7th or something like that. What? Sorry? I need the whole number. Same number, 6.23 times 10 to the positive 6 meters per second. Yeah, it's holding. I can't imagine you making a silliness rate. So for this equation here, Alex, I figure with 5 variables, I can give you any 4 and find the 5th. Turn the page. How do we explain this thing? Well, there is definitely some kind of a force on that wire. Turns out that force depends on 3 things. How strong the external magnetic field is, how strong the current inside the wire is, and how much of the wire is inside the magnetic field. We say this: the magnetic force on a wire, I'll call that FB wire, is Bill. B, magnetic field. I, current. L, length of wire. By the way, in physics, be clever. Never write a lowercase l like that. You'll think it's a 1. Always write your lowercase l's as written lowercase l's, and you'll know that that's a lowercase l. Okay. So, example 4 says, find the magnetic force, magnitude, and direction on the wire. Let's find the magnitude first. The magnetic force on a wire is Bill. Look at the diagram. How strong is the magnetic field according to this diagram here? Look at the diagram. How strong is the magnetic field? Yeah, units, right? 6 Teslas. How strong is the current? 5. How long is the chunk of wire that's in the magnetic field? Not 70, 0.7, yes. You get 21 newtons? That's the magnitude. Now they also wanted the direction. Oh, this is right-hand motor rule. Point your right thumbs in the direction of the current. Extend your fingers in the direction of the magnetic field. Got to bend a little bit for this one. Which way is your palm pointing? So for me, if I do here, boom, boom, I find it easier to tilt my paper up this way, then you can bend a bit. But I'm getting my palm pointing towards the paper, is that right? Into the page? Yes? Into the page. Suppose the force on a 5 centimeter piece of wire carrying 12 amps of current is that big. What's the magnetic field strength? Okay. Well, again, we're talking about the force on a wire. Hello, pen. Just suddenly stopped working here. We're talking about that. That's a typed L. I can't put up with that. Is my pen going to work now? Hey, now I'm back. However, in this case, they're asking me for the magnetic field strength. I guess that's going to be the force divided by IL. Okay. Force, 0.001 newtons. Current, 12. Length, 0.05. You get 1.67 times 10 to the negative 3 Teslas. There's some neat applications of this force on a wire concept. Example 6. Any of you ever see the movie The Hunt for Red October? It's a classic. Yep. So the premise behind it, it was set in the height of the Cold War. The premise is that the Russians have essentially designed a jet engine for a submarine with no moving parts, and it's based on real research. This is how the magneto-hydrodynamic drive for a sub would work. And it would be a very, very quiet engine if it's not already been developed in top secret method, I don't know, because it has no moving parts. Watch. It says this. Run a current through seawater. So here is a picture of our side view of the sub, and the current is flowing. What do those X's mean? Into the page. Now, what are they flowing through? Seawater. Is seawater conductive? Yeah, so we don't need actual wires. What you would have, now what I've got here, and I cut away from the picture, there would be on the front here a very big positive plate, and on the back against the sub a big negative plate, so you have charges flowing from positive to negative. There's your current. So the current is flowing into the page, and which way is this magnetic field here? Magnetic field lines always point from what to what? So which way is the magnetic field in this picture? So point your thumbs into the page. That's the current. Extend your fingers towards south, down the page. Which way are your palms pointing? Are they pointing backwards? Like to the left? All of the seawater molecules would feel a force pushing them out. And since they would feel a force pushing them out, they would apply a force on what was pushing them, the sub. And the sub will scoot forward. Not really fast. You're not going to get like a jet engine speed underwater. But here's the beauty, Justin. No moving parts. Very quiet. Back in the Cold War, the idea was you would listen for the other submarines. This would sound like water. Trying to find the sound of water in the ocean, I guarantee, is impossible. You got nothing to narrow it down. So there's one possible application. All sorts of other neat ones, but here's a very basic one. I mentioned, oh, and you could control the speed very, very easily. How? Well, either increase the current, we can do that. You couldn't really change the length of your sub. Oh, but you could also increase the strength of the magnetic field, because it would be an electromagnet that you would be using here, like a solenoid. Ampere played around with solenoids, and he noticed that the magnetic field strength that a solenoid created depended on three things. The current running through the wire, more current, bigger field. The number of turns of wire, more turns, bigger field. The length of the solenoid, he found the shorter the length, the stronger the field, the longer the length, the weaker the field. It's how densely packed the wires are. In fact, he found this. Turn the page. Magnetic field strength is directly proportional to the number of turns, the current, but it's inversely proportional to how long it is, because the longer you are, the smaller. Very similar to G being proportional to that and electric field being proportional to that, except, Shannon, back in the old days, 2 months ago, to make this an equation, we had to put a constant there. We used a K, 9 times 10 to the 9th. To make this an equation, we put a constant there. We used a capital G, 6.67 times 10 to the negative 11. To make this an equation, we have to say this. The magnetic field created by a solenoid is equal to, leave a small space for a constant, Ni divided by L, and the constant that we put in front is mu naught. You can call it mu zero. My physics teacher in high school, who I still love, was British, and he always called it mu naught. And that's how I learned how to say it. So I'm going to say mu naught. And sometimes I'll even say it with a British accent if I'm really back in my high school days. Where mu naught equals, find it on your sheet. What is it? Tyson, what is it? No, it's on the front page in the constant section. U0. Go find it. It's there. Somewhere below a proton, somewhere below an electron. It's there. Jessica, what is it?
4 pi.
For what? Pi? Pi? What the heck does pi have to do with how strong a magnet is? Like I've said, the universe really seems to like this number. Yeah, it's 4 pi times 10 to the negative 7. And it has one of my favorite names for any constant out there. What's this constant called, Alex? The permeability of free space. What did you learn in school today, Rob? Oh, Daddy, I learned about the permeability of free space. Oh, Rob, you are ever so clever. Isn't that a great sounding name for a constant? Okay. And nerd note, yes, pi rears its ugly head again. No, it rears its beautiful, wonderful head again. There is a second version of this equation. Oh, by the way, where n is the number of turns of wire, I equals the current, and L equals the length of a solenoid. There is a second version of this equation. Sometimes all we know is the ratio between the number of turns of wire and how long the solenoid is. In other words, if your wire has 5,000 turns and it's 5 centimeters long, they might just say it's got 1,000 turns per meter. Okay. And they write it this way. Where n is the number of turns per meter. That's the rating of the solenoid. You realize what this does, though, Shannon? This gives us complete, very accurate control over how strong we want a magnetic field to be. Let's suppose you have 100 turns and you want your magnetic field to be half as big. 50 turns. You want it to be 76% as big? Oh, 76 turns. Like I can be that accurate. Oh, and we haven't even talked about that I can also control the current very, very easily as well. So it gives us very fine control over the strength of an electromagnet. Very detailed control. Example 7. A solenoid is carrying a current of 4.2 amps. If the solenoid is 1.2 centimeters long and is made of 750 turns of wire, what's the magnetic field at its center? Solenoid is mu naught n I over L. I encourage all of you, once we write out this, type this into your calculator, because some of your calculators might not do the 4 pi times 10 to the negative 7 the way you think it's supposed to work. Mu naught is 4 pi times 10 to the negative 7. N is the number of turns of wire, 750. I is the current, 4.2 amps, divided by, oh, careful, not 1.2, because that's centimeters. What will I put instead? 0.012. How strong a magnetic field will there be in the center of the solenoid? And make sure you try this so you know whether your calculator will let you type in 4 pi and then hit the scientific notation button. Some calculators won't. The TIs will. You get 0.33? Yeah? Units. What do we measure magnetic field in? It's the new unit of this unit. What was the units for magnetic field? If you're not sure, turn back a couple questions and read. I'm going to talk about that. Rest of us, though, I still want the units. Huh? Oh, Teslas. Now, if your calculator won't let you enter 4 pi, here's what you'll have to type. Pi times 4, scientific notation button, negative. You got to flip the pi and the 4 around. Try that again. Pi times 4, make sure you hit the times button, and then scientific notation button. Negative 7 times 750 times 4.2 divided by 0.012. Okay, don't clear your screen. Let me look for 1 second. Crisis solved. So this would be, hey, what if I wanted twice as big a magnetic field? Double the current, easy to do, or just double the number of coils of wire when you're making the solenoid in the factory, easy to do. What do I want it half as strong? Cut that in half or cut that in half. You could also change that, but that's a physical parameter, how long your solenoid is. Probably you're stuck with that. But it's easy enough to add or subtract coils of wire. Example 8. Find the field and direction at the center of the coil. In this diagram, you're looking right along like a telescope through the solenoid. So you're looking down the length of it. Okay? That's what that diagram is supposed to be. In other words, Alex, that's the current in the wire going this way. It wants the field, magnitude, and direction at the center of the coil. The coil is carrying 10 amps of current and has 2,550 coils per meter. Okay. Did they tell me the total number of coils here? I'm using that second equation, n lowercase n I. They told me the number of turns per meter. They didn't tell me how long the solenoid was. That's okay, I can adapt. 4 pi times 10 to the negative 7. The number of turns per meter is 2,550. The current is 10 amps. How big will the magnetic field at the center of the solenoid be? You get 0.032? Or am I wrong? Yeah? No? Brandon gives me a thumbs up. Teslas, right? The magnetic field. Direction. Okay, now we have to use our solenoid rule. That rule was, imagine holding the solenoid in your hand. Now, if it's going away from you, I think you kind of hold your hand facing the paper like this, yes? Or like this, I'm not sure what. Oh, curl your fingers in the direction of the current. I think I have to hold my hand facing the paper like this, do I not? Which way is my thumb pointing? Which way is north? Out of the page. I think not up. Up would be that way. I'm getting towards me. Yes? Out of the page. Example 9. Suppose you're a factory that's making solenoids for cars or whatever. It's to be wound on a cardboard form 30 centimeters long. How many turns of wire are needed if I know that I need a magnetic field of 6.28 times 10 to the negative 3 Teslas, and I know that the max that my wires can handle is 5 amps before they melt? And now you're actually customizing your factory building of the solenoid. Okay. We're talking about the magnetic field of a solenoid, which is mu naught n I over L. I know to use that because they didn't start talking about turns per meter. They gave me the total number of turns and the total length. Courtney, what do they want me to get by itself here? Oh, okay. N is going to be BL over mu naught I. Yeah, I think? Oh, good. Let's plug and chug. 0.00628. L 0.3. Mu naught 4 pi times 10 to the negative 7. I 5 amps. How many coils of wire would I need for this to function? Sorry? Even? Almost. I think I tried to make it so it's like 299.9 or something, like very close, yeah? So 300? So again, this gives us a very customizable way to build an electromagnet to whatever electric field strength you want. Okay. What's your homework? Here's what I assigned my last class. We did 1, 2, and 3. Now, if you take a quick look at number 3, they're talking about a helium-2 plus. A helium-2 plus ion is 2 protons. What's the mass? 2 protons. What's the charge? 2 protons. So use 2 protons. So 1, 2, 3. 5, 6, 7, 8, 9, 11. And then hang on 1 second. 1, 2, 3, 5, 6, 7, 8, 9, 11.